is, so which is the closest sample that can, the average sample that is closest. What they're showing is that the closest sample has to be further away, when they apply distillation. Okay, that's basically what this means. And, yes, okay. And the last thing is, I found it interesting because it's about confidence, and we spoke a lot about confidence. They use a very simple measurement of confidence. We know now a lot of measurements of confidence, but they use the argmax, so the size of the argmax. They say that for endless it doesn't make much sense because the accuracy is so high that all the activations are very high. But here what they show is that on average, as you increase the temperature, the confidence of activation is higher, which is an interesting result because the more the temperature, you're forcing these to be flatter. You're trying to force these to be flat, but when it gets it right, it's actually with very high confidence. Does that make sense? Because otherwise, yep. So those are the results, and they, I think they are quite interesting because we were discussing before. It seems like almost like they solved the problem of this particular adversarial sample. They make a long discussion, which I find interesting, but there are only 2 points that are sort of non-trivial. The first one is that another thing that we were talking about before is that, well, why instead of going through all this trouble, why not just make those targets soft instead of hard targets? So you put 0.9 in the actual class and then divide the rest of the probability in all the other classes. And they say they attempted that, but yeah, they didn't get a lot better. So they only had a small improvement, a marginal improvement, whereas with this they got a very big improvement. They say, so the misclassification rate of adversarial samples was 86%, so they could still get a very high adversarial success. Yeah. And the other interesting thing that they say is that this method is actually very robust because even if the attacker knows that this is being used, it's not clear how to overcome it. So I think that's a bold claim. But if any of you can think of a way to overcome this problem, that would be interesting to see. Yeah. That's the paper. Any comments? Temperature related.
Do they give any suggestion as to what heuristics should be used to choose a temperature?
Well, yes, they gave all these
Just
that are temperature related. Yes. So yeah, it's basically apparently the bigger the temperature is always better. But of course, you have to go to a point where it doesn't affect your accuracy very much, right?
You mentioned that they tried to do it without simply by putting it to 0.9 and everything else to 1 over
2.1 over
yeah.
n minus 1.
What is the roughly equivalent temperature, right? Because we know a temperature of 100. I would almost think that by that time the soft targets are almost equally distributed, except for one that is slightly darker. So the question begs is then, if you would, instead of having only a 0.9, have like a 0.6 or even lower as the leading, would then we get similar, because we see if we go back to the figure, initially the increased temperature also does not have that steep of a drop off, right?
Where?
Yeah, and right, so initially it's pretty flatlining, right?
Well, yeah.
And well, a temperature of 5 is already quite high, right?
They also they say that
this is a logarithmic scale,
point.
so this is a logarithmic scale, so the drop would be much steeper if you join.
So they do make a discussion about that in the
The
other
Y
one.
scale is not logarithmic, right? No.
Sorry? This one is log.
So the
That
5
one
is
is
pretty
not
far
log.
away.
I mean, they speak of this elbow point as the point where that happens, where the temperature is so high that you're basically trying to force the network to learn a flat distribution, which is where you get the biggest success rate, but
it's still
your accuracy can drop.
But it's still surprisingly accurate then, right?
Yes, it is. Because the ones that you get right, you're going to get them right anyway, right?
It would be just, I think there might be a bit comparison apples and oranges with the not temperature distillation, but just regularization. I think if you regularize harder, you might get similar results.
They also speak about regularization. They say that, So they don't compare to regularization techniques because regularization is based on your loss function.
Yeah, I mean the output.
And
of
this is not based on a loss function, but more on like a crafted attack, something that is designed to destroy the network. So it's quite different from regularization, but you might get something similar from trying to regularize on these gradients. So on the gradients that they show here, which is not a very. So if you try to regularize on these gradients, then you might get a similar outcome. But that's what it is doing, right? 1 over t is basically forcing these gradients.
So it would be interesting to have an idea of what the soft target profiles actually look like at a temperature of 10. Is it still very flat, or is it quite?
I mean, the problem. So the only problem that I see with using this sort of let's manually make the soft targets is that you're basically making all the soft targets the same, right?
Yeah, you lose accuracy, absolutely.
Yeah. Whereas with the temperature, it sort of learns what the soft targets should look like.
But you have a second model to train, so in principle. But it's just interesting to understand why it actually works. What's really the driver?
Well, remember it gathers structural information as well.
Yeah,
exactly.
So if you're wanting to differentiate 1 from 7, for example, that's a different question than differentiating 1 from 8.
But does it help with the adversarial attacks? That's the question.
Yes,
The problem
because
would.
it's a lot easier. So if you wanted to make an adversarial attack on a 1 versus a 7, it's a lot easier to make it than versus 1 against an 8.
Yes.
So by gathering this structural information, the network can understand what the ones look like, what the whole
But wouldn't that make it actually more susceptible to adversarial attacks? Because then the newly trained network also would be able to kind of poke into this direction.
Well, no, because of this, because you are minimizing the change of the output with respect to the input.
Yeah.
So this is your strong regularizing assumption that
It's really hard to say because that's the change in size as well. So it's really hard to say whether this actually is small or roughly the same or large.
So the whole point is trying to make this flatter.
Yeah.
And that's what that temperature coefficient is trying to do, is to make that as flat as possible. So you need a big adversarial attack, so big that anyone can recognize it. Yeah. No questions?
What was the connection to the theorem? I didn't quite got the reasoning how that theorem means that adversarial attacks are not.
It's not very related. It's just trying to prove why generalization, why distillation generalizes well.
Okay.
And why it, so in theory you generalize better if you're, so that should also be a 1. So a model that cannot distinguish between that one and that one is not generalizing properly.
Yeah.
So you would say that a model that is robust against adversarial attacks generalized better than one that is not robust. And they use that as an argument to prove that distillation actually generalizes well. Yeah.
I wonder, you mentioned about using surrogate functions at one of time. Do you know much about that, and how does that, if you don't know the weights, how do you launch an adversarial attack?
So you can test this. So normally this is something that's publicly available, right?
Yeah.
So
you get a black box.